Right. So this is module 3. And as we go through this module, I'm going to show you formulas as well as how to do it with the calculator. But I expect you to use the calculator. The calculator that the book teaches and what I'm going to show is the Texas Instruments BA2 Plus. You can use the student or professional, it doesn't matter. If you don't want to buy the calculator, that's fine. If you have a smartphone, there is an app or several, I'm sure, for it. The one I use is called BA Calc, capital B, capital A, and then CALC, like calculator. That BA Calc is an emulator. So everything that we're going to do with the calculator in this entire course, not just this module, you can use that app for. There are also some web calculators. Just I don't know how all of those necessarily work or exactly how the data needs to be put in. But you're also welcome to use that or even Excel. Later on, there will be some Excel problems, and we'll talk about how to enter the formulas in Excel. There are also those SimNet Excel problems to get you familiar using Excel. But it's also good to learn the calculator if you plan to take professional exams that will use time value of money. That's because things like the CPA, CMA, CFA, CFP exams do not allow you to have a programmable calculator. So you can't go in with like one of those big graphing calculators, but you can use this financial calculator where most of the formulas you would need are already built in, right? So that's the advantage of the calculator is for professional exams. It's also good in meetings because you don't necessarily have your laptop, so you could always just pull out your calculator and calculate some of these things sort of on the fly. But as far as in an office setting, obviously, when you have more robust data sets and you're doing much more complex calculations, Excel will be the way to go. But it's good to learn both. The formulas I'm showing really just because I want you to understand there is a formula and you can see what it looks like so you can understand the different pieces of it. But please don't think that you need to do the formula for me. Okay, so this first one, I showed 3 different problems on calculating present value, right? The first one, we're told we have this future amount that we're going to receive, right? We're told that it's 73 years in the future, right? So T is 73 or N is 73 on the calculator. We have the interest rate, right? We're assuming 11% is the discount. And so we can calculate the present value. So there's a present value formula. Present value is equal to the future value divided by 1 plus r to the t. Or you can just put it in the calculator and then we'll solve for PV. You notice where it says PMT. Oh, let me just explain all of those. So N is the number of periods. I/Y is interest rate per year. The PV is present value. PMT is payment and FV is future value. If you know any 4 of those, you can solve for the fifth. If you notice the payment is blank, you can put payment of equal to 0, right? In our particular case, there's no intervening cash flow, right? We just have a lump sum at the end of 73 years, and we're saying, what is that today, right? And there's nothing happening in between. We're going to have some problems where we're focused on like what is a payment for an auto loan or a mortgage, that type of thing. And so we'll use the same approach with the calculator. So, and as we go through these, as the problems become a bit more complex, you'll quickly see how the calculator makes it far easier, right? So, oh, and then these 3 problems. The first one, we're looking at annual. Um, so it's 73 years, right? And that's what we're solving for. For the next one, we are looking at months, right? They tell us it's 9 years from now, but they give us this 0.5% or 0.50. We would actually in finance normally say 50 basis points, right? If you ever hear that term basis points, it's just a percent of a percent, right? So 0.50% per month is 50 basis points per month. When we would put that in the calculator, it would be 0.5, right? Like that's how we'd enter that. And we're just going to calculate what do we need to deposit today to have this amount in those 9 years. And we just take the 9 years and convert that to 108 months. 9 times 12 is 108, right? And then the third one, right, we're going to have this future value of $96,000. It's 7.5% as an annual rate, but it's compounded daily. So what we're going to do is say 6 years times 365 days, and our interest rate of 7.5 divided by 365 days, right? And so it gives us this daily rate, right? And then we'll calculate what the present value is. Okay. And so in this case, the big difference between that first problem and that last problem, right? Because it's like it was over 6 years. Why wouldn't you just say n equals 6, IY is 7.5? And it's because you have compounding going on every single day, right? And so we just need to compute that. That first one assumes the compounding happens on an annual basis. So it's compound interest, but it's annual in the first case. It's daily in the third case. Okay, so just as we did this and solve for the present value, you can solve for the future value, right? In this particular problem, we are told that we have 6 deposits, the first birthday through the 6th birthday. And then after the 6th birthday, with no more payments, but at the age of 65, you're going to receive $420,000. Okay. So if we assume that the interest rate should be 12% for those first 6 years, and then you have 7% for every year thereafter, right? What is the value of the child's policy when they would receive the 420,000? So it's a way to look at, is this an investment you want to do, right? So the formulas are there. Instead of focusing on that, I'm going to focus more on just doing it in the calculator, right? So you would just take that first payment of $880, and we're going to move everything to year 6. So if that's the first birthday, then I need to grow that at 12% for 5 years and calculate that value. And then the next 880, let it grow for 4 years and calculate that value. And then the 980 for 3 years, the 980 for 2 years, and then the 1080 for 1 year. And then on year 6, there's no growth. It's just the 1080. So we'll just add 1080 plus what all of those future values are to give us the total payment that you would effectively have at year 6, right? And so it's going to grow at 7%. You're going to be 65, so we would say 65 minus the 6 years already leaves 59, right? And then calculate the future value, and it turns out it's a little bit higher than the 420, right? And so we would say it's not worth it, but this is assuming I can guarantee 12% for 6 years and then 7% after that, right? But assuming that all holds, you would say no, don't do this type of policy because you're not going to receive back what it would be worth. Okay. And this is another problem, but you're looking at someone has a collection of silver dollars, right? They bought the dollars for $1, right? Because that's back when silver dollars were just in circulation, right? So, and if we assume that this is going to grow for 110 years, and then the value appreciates at 5% a year, then what would that $85 be worth, right? And then you can put this in the calculator, right? The 110 years for N, 5.1% growth for IY, $85 for the present value, and then 0 for payment because there's nothing intervening, and then you'd compute FV, right, to solve for the future value. And then the second one, you just made your first $4,500 contribution. Assume you earn 10,000, or sorry, 10.7% interest, and you're not going to make any further contributions. So you're not really making a payment. You just have this lump sum, right? So it's 4,500, and we're going to let that grow at 10.7% for 41 years, right? And then we're going to say, what is that worth today? Right? And then you just do the same thing for 31. And then compute the future value, and you'll see the difference, right? And that's that the value of contributing early, right? Okay. And so this type of problem is referred to as time value of money. But anytime you see these tables, and I grabbed a couple of examples here, one where you're solving for present values and ones where you're solving for future values. But as you do these problems, you'll just become, becomes a bit routine after you practice it for a bit. And you'll find that calculator saves you a great deal of time. You can also solve for years and solve for interest rates the same way, right? You would just have a different data that you enter, and then you would solve for it. Again, if I know any four, I can solve for the fifth one. And here's an example of two problems where you're solving for the interest rate, right? So in that first one, right, you want to make payments, right, of 600 pounds, right? And the 600 pounds are also going to generate 68 additional pounds each year, right? So we have a lump sum to start with of 600, and we're going to add 68 a year for 30 years, right? And remember that payment goes back in, and it's going to keep the payment's going to occur over this entire 30-year period, right? And then we're going to compute what is the interest rate from that, right? And then it's 10.8%. You notice on this one, there's nothing for future value. The future value is zero, right? And this would be just like if you said, hey, I took out a loan of $600. I'll say dollars, not pounds, so it's not as confusing. I took out a loan of $600. I'm making payments of $68 a year, and I do that for 30 years. What is my interest rate that I'm paying, right? And you would just solve for it that way. And then the next one is a little more complicated just because we're going to talk about APR, right? And so in this particular case, I'm borrowing $72,000, right? That $72,000 gives me a payment, the only thing I can pay on that is $1,300, right? So I want to basically take out a loan, just like when you show up at the dealership and you point to the one you want, and you're like, this is all I can pay. And they start trying to change. Well, maybe we do it this number of years instead. Maybe we can, So those types of decisions are what drives, us solving for different pieces, right? And so in this case, we're doing a 72-month APR, right? So what we're going to do is say, okay, I know N is 72 months. I know I'm borrowing $72,000. I'm going to pay $1,300. Once I've completely paid off this loan, the future value is zero, right? I'm not going to, it's not, yeah. So it'll be paid off completely. And then what is that interest rate? And if you notice that interest rate's really small on the calculator, right? That 0.755, that's the monthly rate, right? So we would just take that rate, multiply it by 12, and that gives us 9.06 annual, right? And we're going to do a problem in a bit looking at APR versus effective annual rate, which takes in consideration that this one is compounded each month, right? But the APR of 9.06. As long as it's below that, you could afford the loan. This is calculating rate of return. So we have a present value and we have a future value. There is no payment in between. So that's just going to be zero. We're told the number of years, right? And again, we would just solve for IY, right? So anytime we're solving for the number of periods, it's in, regardless of what the types of cash flows it is. And if we're solving for any sort of rates, it's that IY, right? Because the present value, payment, and future value, those are all dollar values, right? So before we were using this to calculate interest rates, this one we're calculating rate of return, right? But it's the same type of calculation. And then in the second one, again, it's like that problem we had with silver dollars. This one is silver half dollars, right? So you have, it was worth half a dollar, right, to begin with. And then it is sold later for 209,000. And it's 129 years between the two events, right? And we would just solve for what is the interest rate. And that gives us the rate of return on holding that silver half dollar. Okay. And I mentioned this annual rate versus the effective rate. So we like to talk about annual rates because it's when we're comparing loans, uh, the bank will give us quotes using that annual rate so that we can look at things that are monthly versus, locking up for say a solid year, that type of thing. Um, and so in this one, there's a perpetual annuity paying 2,800 monthly, and it currently sells for $328,000. Now, present value of a perpetuity is equal to C over R, where C is that coupon payment, or the contract here pays 2,800, right? And then we would divide that by R. In this case, we're solving for R, right? So we're going to take that 2,800, then divide it by the current market price of $328,000, right? And that gives us 0.85% each month, right? And that's because we have a monthly payment. Okay. So if it's 0.85 per month, you multiply that by 12, right? 12 months in a year, and that gives us our annual percentage rate, which is 10.24%. However, if I have a annual contract versus this monthly contract, it's a lot more, right? Because I've got this monthly thing going, right? So I need to make sure I'm talking about the same thing. So whenever you're looking at those, there'll normally be like a little asterisk, and then down below, they'll tell you what the effective rate is given the compounding frequency is, monthly, or with credit cards are daily normally. So the more frequently it compounds, the bigger deal this is, right? And so we would calculate the effective rate is 10.74%, right? There's about an extra 50 basis points in there because of it being monthly compounded. Okay, now if you want to calculate how long it takes for something to double or triple, right, we can do the same type of calculation, right? They're going to triple your money in 24 months, right? And then the question is, what is the rate for every 3 months, right? Every 3 months, right? So 24 divided by 3, right, gives us 8. So it's 8 periods of 3 months each, right? Which 24 months is 2 years, right? 8 quarters is 2 years, right? I mean, so hopefully that's pretty straightforward. And we're just saying it's going to triple, so we're going from $1 to $3. And so we would just solve for that interest rate, which means they're saying we're getting 14.72%. But keep that in mind, right? If you had 14.72%, then in 8 periods, it would triple your money, right? So that's we start hearing these numbers, that gives you an idea of how large some of these must be. Okay, and I'd said about the perpetuity, is equal to C over R. A perpetuity never dies; it never runs out, right? These are annuities. Annuities have a set number of years that they'll go for, right? In fact, this one, it's 8, then 40, then 26, then 15. You see it in the table there. So again, I show the formula so you can calculate, what the um, payment would be. But in our case, just use the calculator, right? Um, excuse me. The present value for all of these are equal to zero, because what we're saying is um, you're going to have these annuity payments, and we know that the future value at the end would be $25,000 or 1.1 million. So you understand the future values. We're saying this is what that total annuity would be worth, and the question is, what are the intervening payments, right? And then they each have their own interest rate and their own number of years, and so we're just solving for what is the payment. Okay. And this is going, again, we're going to calculate a payment, but what we're saying is uh, you have an individual, it's a pretty long problem. So feel free to just pause and read through it. But basically, you have an individual, they have money sitting in bonds, they have money sitting in stocks. You're going to you're going to continue to put money into it for the next 10 years. Um, and as they each have their own returns, right? And then that is going to end up being some amount of money when you reach retirement, right? And I'm assuming my retirement is going to last for 25 years, not one day longer, right? And so I want to withdraw the money so that I run out of money in exactly 25 years, right? And so the question is, how much can I pull out of my account each year of those 25 years, given that I'm going to continue to receive interest, right? That money's still invested in an account as I'm withdrawing from the account. So given that it's going to generate more money on its own as well, right? Given all of that, then what is my annual payment to myself, right? So we're going to do two time value money calculations to begin with. One to grow the bond account, including my additional payments in, right? And then what is the future value of my um, stock account, right? And then you add those together. That's how much money I have, and then we just solve for what would my payment be given I want no future value, right? FV is zero, right? Now I could say, and I want to leave an additional $50,000 to my heirs, then your future value would be 50,000. You would compute a different payment, right? But in our case, we're wanting to take all of the money out um, in equal amounts over 25 years. Okay. We did a problem earlier calculating the rate given it was going to triple in a set amount of time. This one, we're calculating how long it takes to double or quadruple an investment, right? So again, we're going to say from $1 to $2 or $1 to $4. And this one, they're giving us the interest rate, and then we're going to solve for N. The last time they gave us N and we were solving for the interest rate. And it was tripling, and this one is doubling or quadrupling. Quadrupling is just doubling, right? And so once you calculate the doubling rate, it should be twice. Now, in this case, there's because of some rounding, it doesn't show that, but you would expect it to be twice the amount of time to double, as to quadruple, and then that amount of time will take it 8 times, and then you do that amount of time again, it'll be 16 times, right? And then 32 times. And this is why we always tell people to start investing as early as possible, right? You want that money out there for the greatest amount of time, because this time value of money will really help you going forward. Here's two more problems where we're solving for the number of periods for something to occur. So this first one, someone owes us money, right? And we calculate how much they owe us, and they tell us what they could repay, right? And we tell them that, we're going to continue to charge this because of the overdue balance, right? That's what that interest rate is, right? and then we would solve for what is in. If the future value is equal to 0 in this case, because they're going to pay it off, right? So at the very end, the future value is equal to 0, right? And then we solve for n. What they gave us was a monthly rate, right? That 1.04. So what we solve for is a number of months. For the second one, I'm going to receive $34,000 at graduation in 2 years. I'm going to be able to invest that at 10%, and then I'm going to let it grow until it reaches $169,000. And so the question is, how long would I have to wait for it to get to be that growth, right, from 34 to 169? And so the number of years for that is 16.82, but then I have 2 more years until graduation, right? So I just have to add 2 to that. A little bit of a trick question there. Okay, and then the last one here is amortization of a loan. So they told us that the loan is $72,000. They told us that the interest rate is 9%, and that and we're going to make equal payments for each of those years. And then what we're going to do is calculate what is the total interest paid. So we know it's $72,000. We know interest rate is 9%, and it's going to be 3 years, right? N is equal to 3. And when we reach the end, the future value, see their ending balance is going to be 0 at the end of year 3, right? So PV is 72,000, future value is 0. IY is equal to 9, N is equal to 3. We would just solve for payment, like compute payment. And then that would give us what the total payment is. So that $28,443.94, we pay each of those 3 years, right? And so we would say each year, what is the how much is interest? So it's 9% of 72,000 the first year, right? And so that means I owe 6,480 in interest, but I paid 28,000, right? So take the 28,000 minus that 6,480, and that gives you how much went to principal. The beginning balance minus the principal payment gives you the ending balance. So that's where each of those pieces are coming from. This one is just 3 years, and then you see how those get dropped in. But you could do this for 360 months of a 30-year fixed rate mortgage, right? And that's what an amortization table is. It's just you create this table of payments. As you can imagine, this is much easier to do oftentimes in Excel, right? Because you just type in the formula and then you kind of drag it. If you notice, the beginning balance in year 2 is the same as the ending balance in year 1. Same thing for beginning balance year 3 and balance year 2. So just to make sure you understand how all these things connect. And as you see, I make the same payment each year, but the amount that's going to interest is going down. The amount going to the principal is going up, right? And that's why you can have a loan for a while, and it seems like you've been paying on it, paying on it, paying on it, and the amount that you owe just doesn't seem to be dropping, because it doesn't really drop quickly. But then once it starts to drop, it does pick up speed very quickly, and so that's what you're seeing here. Okay, and that'll be it for module 3. Module 4 picks up with a bit more of the time value of money information. And also remember, in module 4 we'll start having the SimNet, and so you will have some time value of money problems that you're going to need to do with that Excel sheet, right? But you'll see that for very simple problems, Excel seems like a bit of overkill and it'll take a lot of time. But when you have a more complex problem, the flexibility that Excel gives you is really good. So being able to do it both with the calculator and with Excel will be worth it to you when you're done with this course.